So let's start with a sequence of 3 speakers from Japan, from the Earthquake Research Institute, and they will present us all the aspects of the earthquake and the tsunami. The first speaker is Dr. Hiroshi Sato, and the title is Geological Background and Earthquake Sequence of the 2012 Tohoku Earthquake, Japan. At the end of each speech, there is a very short time, 3 minutes, for questions.
Okay. Yeah, thank you. Okay, thank you. First of all, as a Japanese, I would like to express very much appreciation for the various kind of support for the international. And we will never forget this warm hearts. Thank you very much. And today I would like to provide the geologic information as a background of these earthquakes, and also the sequence of the seismicity. And okay. Okay, northern Honshu, Japan, excuse me, forms the classical example of the trench and arc and back arc system. And the almost 110 million years very old and cold slab being subducted beneath the Tohoku, northern Honshu. And the present day, the arc itself receiving a strong compression. And especially the back arc region are characterized fold and thrust belts. And this arc's history is relatively simple. In the early Miocene, it's lifted away from Asiatic continent, and so the Japan Sea constructed, and also as well as the aborted lift and the some extensional feature prevail in the arc itself. However, in the for side, it's relatively stable, and since the Pliocene, this arc receiving a strong compression, and all the lift system is inverted as a normal fault reactivated as a reverse fault. And simultaneously, the forarc side sunk to a very deeper part associated with a strong compressional deformation. And that is the crustal section of from trench to back arc. And the thickness of crust is continuously thinning toward west. It's a remnant of the previous Miocene back arc extensional deformation. To compare with, and also since the volcanic activities keep going, and lots of underplating has been occurred, just actual part of the volcanic arc. And however, also again, the forarc side is very stable. Yeah, however, to compare with the younger subduction zones, such as the Nankai Trough or southwestern Japan, the development of the accretionary prism is very poor, and mainly the tectonic erosion has been keep going since the Pliocene. And so we have some diagnostic problem between the horizontal strain rate measured by the geodetic and also geologically estimated. And the geodetic measurements, triangulation and also GPS suggest almost on the order of 2 minus 10 to 7 per year strain. Yeah, however, geologically determined, it's only 2 to 10 to minus 8 per year. So it's very small to compare with the geodetic measurement. And a similar diagnostic problem also observed on the coastal vertical movement. That is the tidal measurement, and for several decades, it's keep subsidence. The rate is commonly larger than 3 millimeters per year. However, we have developed well-developed coastal terraces. And for example, one of the surface dated about 112.25 kilo-year is well preserved in a higher level, and the long-term uplift rate is estimated as the 0.3 to 0.6 millimeter per year. So it's very diagnostic because in a short time, this area showing the strong subsidence. However, as a total, we need a very gradual uplift for a long period of time. And so, in short, to take into consideration about the time scale range, that geologically the strain rate is much, much smaller. And also, even though they measured coastal subsidence, or geodetically measured, but geologically, we need a gentle uplift. Yeah, so that means the large amount of strain release is needed along the subduction interface. And shifted to the tsunami deposit story, and before this tsunami comes, that since the late 90s, as well as the Cascadia or Chilean margins in Japan are the same, and the very good works has been done for on the tsunami deposit. One example is that is the Fukushima prefecture, and the site, we call it geoslicer, and you can see the several yellow colored sand layer is marked by the marine fossils, and also that is outstanding that within the peat we can recognize that kind of sand layer that I believe is derived from tsunami. And that is a dating of this site, and the earliest one is correlatable for the historical document that dated about, and correlated 869 Jogan tsunami event. And also several tsunami deposits are dated, and as a total, 4 or 5 large tsunami events we can observe for 3,800 years. So roughly speaking, that's the once in 1,000 years we have that kind of tsunami attack. And that similar type of research already carried out by that's close to Sendai and Sendai Plain. And Geological Survey of Japan intensely studied to observe to find out the tsunami deposit. And that satellite image, that a little bit dark colored part, is a submerged area by the tsunami attack. And this portion, especially the red color, represents the distribution of tsunami deposit. And so that means the submerged area is pretty much similar, so suggested by the distribution of the previous tsunami event, correlated to the 869 Jogan tsunami deposit. And however, the basic strategy to evaluate the long risk for the subduction megathrust is basically depend on the instrumental recorded earthquakes. And so the commonly such kind of circuit area is marked to the possible asperity or possible source area. And so the present day's evaluation is maximum magnitude around 8. And nobody expects magnitude 9 earthquakes. Yeah, however, they are trying to involve the result of the paleoseismological records. However, unfortunately, that is not in time. And so tsunami comes, and it's ruptured around the very large area of Tohoku coast. And the detail I'm expecting explained by the Professor Kato, so that I'm gonna not go into the detail. However, the result was pretty much horrendous. And in terms of seismicities, is that green color events circle. Oh, I have to hurry up. And is a previous one. And the red color is the aftershocks, and the blue the foreshocks event 2 days before this large earthquake, magnitude 9. And from the correlation between the structure and the location of the ruptured area is I will see this seismic line here. And the rupture started, so mainly 2 segments. One is very flat and the other are relatively steeper. And the main shock started to this around the corner, and the ruptured very much looks like flat area. And yesterday we have an earthquake, and I expected this deeper part slip, but the magnitude 7.4 earthquake seems to be in a intra-slab earthquake. So the nature is not so simple. Anyway, and starting this foreshock, and then 2 days after, the rupture propagated bilaterally, and the ruptured whole area, especially a little bit steeper part is included to the aftershocks. And the termination is, southern termination is structurally understandable, because the southern part is Philippine Sea plate is being subducted onto the Pacific plate. And so that we have a surface triple junction here, and the deeper triple junction, actual triple junction on the northern part. And that is the contours of the north leading edge between the Philippine Sea plate and the Pacific plate. And the seismicity had stopped of this part. And so actually that kind of structure controls to prevent the rupture propagation to the south here. And finally, I will try to, oh my gosh, that's a movie. I sacrificed last night. Doesn't work, so it's a very pity, but okay. As a summary, it's very simple. And to evaluate the risk of subduction megathrust, we have to handle the records covering longer time period. To understand the whole processes of strain buildup and release in subduction zone is really needed. Thank you very much.
Okay, we have time for a couple of short questions. And this is being webcast, so we will need to do microphones for any questions. Yeah.
Thank you very much for the talk. I want to ask why there was this 7.4 earthquake yesterday. It was intra-slab, done deep. Why did we have it? Because I know the reason, and then
You know the reason?
Yes.
Yeah, don't ask me. That's,
okay. And then I wanted to raise that there is a patch left unbroken. A magnitude 7.8, 7.9 is expected. And this patch is so resistant that doesn't allow rupture continue down deep. Then the slab wants to go down and breaks that part. Thank you.
Yeah, I will ask you in the poster session or, okay.
Okay, are there any other questions or comments? Yes, one here, Gara.
Thanks a lot for your great talk. Quick question. You said that the historical, paleoseismological, whatever, the strain height from the past are 1 order of magnitude smaller than the recent ones. I reckon the recent strain rates, the GPS ones, are corrected for elastic deformation. So why do you think is there an order of magnitude difference?
Excuse me, I cannot well understand what you are questioning.
Sorry for that.
Sorry, my poor
you talked about the geological strain rates of 10 to the power of -8 to -8.
Yeah.
And you talked about the GPS strain rates of 10 to the power of -7.
Yeah.
What do you think is the difference?
Yeah,
what's the mechanism?
Yeah, difference is the, so commonly the plate interface is locked. And so the certain amount of time, the shortened much faster. And then large amount of component released. And the remnant is preserved as a geological non-elastic deformation. Yeah, and so that's...
Okay, thank you very much.
Let's stop here now and go to the next speaker. So Dr. Kakuzi Kotetsu, the same institute. The title is Review of the Rupture Process and Ground Motions of the 2011 Tohoku Earthquake, Japan. So it's a complementary aspect, and so you can ask questions related probably to both topics later.
Thank you, Chairman. I would review the recent preliminary results of the rupture process and ground motions of 2011 Tohoku earthquake. And I'm sorry that my material has not been prepared well in such a critical situation. And this slide shows you the aftershocks for 24 hours after the main shock. And these depth contours indicate upper surface of the Pacific plate from this velocity structure model. And we think the aftershocks for 24 hours may suggest the source area of this earthquake. So we put this fault model for the source fault of the earthquake. And we have 3 magnitude 7 class aftershocks, and the 4th one occurred last night. And so, but this is a different type of earthquake occurred outside the Japan trends. So we include these 2 major aftershocks in the source area model. And in previous inversions, we assumed this very simple single plane source fault. And this is hypocenter determined by the Japan Meteorological Agency. And, but this location is a little deeper than this fault plane, so we assume the rupture initiation point to be located around here. And this source area, according to the standard scaling law of plate boundary earthquakes around Japan, a little bit smaller than the extrapolation of this standard scaling. And we have the 4 kinds of data sets for source inversion of this earthquake. First one is teleseismic ground motions, as you already know well. And these are distributions of station we used for inversion. And this is an example of the ground displacement seismograms. And you can see that we mostly use the P-wave data, but big P reflections were coming immediately after this P wave, so we calculated synthetic seismograms of both the phases. And the second data set is strong motion data set. We have the two major strong motion networks called the KNet and KICKNet, operated by NIED. And these small circles of stations of these networks, you can see that this is a distribution of peak ground accelerations. And the maximum peak ground acceleration is over 10,000 gal 1G. And this is a distribution of peak ground displacements. And the maximum is over 100 centimeter. Third data sets are static displacement observed by GPS receivers operated by a Geospatial Information Authority of Japan. And these arrows indicate the static displacement measured by the difference between the average between the 2011 March 1st to 9th, and after the main shock, this period, we should avoid the after earthquake deformation, so we take only 3 hours for post-seismic average. And the fourth data set is tsunami, and we have these data will be presented by Professor Kato in the next talk, but just show the data. These observed tsunami waveforms by these two pressure gauge in the cable system, and we also have these tsunami waveforms observed by GPS tsunami meter invented by Professor Kato. And this slide shows you our point source analysis using the waveforms of the W phase. This is our solution. You can see that this is a deep slip event with reverse faulting, and actual foreplane should be this one. And you can see that this dip angle is quite low. And this solution is very consistent with those by USGS and global CMT solution. And this map shows you which location give us the minimum variance in this region. And we think that as the rupture initiate point, we already defined give us the best solution for double phase data. And such a huge data set, these blue and red circles indicate the KNet and the KICnet stations I have already described. And we pick only these red stations along the Pacific coast, and I made these record sections of ground displacement. And you can see that three distinct seismic phases, seismic pulses, and blue one, and the purple one, and green one. This record section indicates us that the locations of generation area of the first two seismic pulses is around here, and the third one was generated around here. And geological data, GPS Crustal deformation data also indicate the slip distribution. And these larger arrows indicate the asperity or area of the large slips are located around here, and these small arrows are not indicate another location of large slip area. And finally, I'll show you the results of the inversions. And this is a result of a teleseismic waveform inversions. And this is that for the slow motion records. And this is the inversion of geodetic data. And we finally carried out during the inversion of these three data sets. This is a result. And two large asperities I indicated in the previous slides are located around here, first one and second one. And the third asperity is located here. So Rupture first propagate to this direction, and then propagate to this direction. And after that, went westward, reached to the third asperity, like this. For tsunami inversion, we need another law close to the Japan trench. So we did not include the tsunami data for joint inversion, but we can compare the result of joint inversion and the tsunami inversion. You can see the slip pattern quite similar, but most slips are going to westward or upward on the surface fault. So maybe the final result should be compromise of these two solutions. This slide shows you the peak ground accelerations and the velocities and displacements of black ones are those for this earthquake, and the red one are those for the 2003 Tohoku earthquake with magnitude 8.3, only 8.3, but you can see the data for two events quite similar, except for longer period ground displacements. And finally, I'd like to show you the last night's JMA magnitude 7.4 aftershock. And Sato-san already told you this should be an insular event. And sorry, location is around here. And maybe the centroid was located around here. So this should be, and the deep angle are very steep. So this event should be an insular event. And if this earthquake is a plate boundary event, it should be a direct aftershock of the Tohoku earthquake. This means a large aftershock occurred in a large slip area of the main shock. But this is contradicted with the theory. But it is not plate boundary event, insular event, so I think that our solution is still okay. Oh, that's all. Thank you very much.
Thank you very much, Dr. Koketsu. Questions? Please.
Thank you very much for the talk. In the slip inversions that you had, why didn't you cover the near trench areas? There is a curvature. Always this model that you parameterize, there is a distance between the trench and the beginning of the model, while the biggest slip had been very, very close to the trench.
Yeah, actually, this is a very preliminary analysis. So if we put another area in this region, so this cross over Japan trench, so I think it is not reasonable for source fault modeling.
Okay, thank you. May I ask you a question? Just a short one. So in all the inversions that you show us, the joint inversion, but even the individual inversion and also the tsunami inversion, it's possible to see that the maximum slip on the source was in the order of 40 meters or so. Do you have any experience of such a big slip amount in other earthquakes or something? Because it seems very exceptional to me.
No.
Okay, thank you. So let's move to the third speaker, Professor Teruyuki Kato, still from the Erie University of Tokyo.
I know. Okay, thank you very much, Mr. Chairman. Good morning, ladies and gentlemen. Succeeding to my previous two talks, I'd like to talk about the crustal deformation and the tsunami observed by this large earthquake, and also show you some of the results of modeling from this data. And finally, I will briefly touch on the tectonic implications, but maybe this would have some overlaps with talk by Professor Sato, so it should be very brief. Another note is that this is not just for my own research results, but I asked some other contributors to provide me that, some of the results. So I'm just representing the people who contributed to my own talk. So first of all, I'd like to show you some of the results of observation of crustal movements, mostly observed by GPS. As I think many of you already know that Japanese islands are covered by a dense GPS array of more than 1,000 continuous recorded observed GPS. As Professor Sato already showed you, sorry. Oops. Japanese islands are covered by a number of plates, and Pacific plate and Philippine Sea plates is subducting beneath Japanese islands, and those creates a so-called large interplate earthquake offshore of Japanese islands, and that creates large tsunamis. So we have suffered from these earthquake and tsunamis in the historical ages, but the earthquake occurred in March 11 was much bigger than what we expected and we have experienced. So that was really devastating, not just for people, but also for scientists. And as you see here, this is not crustal deformation observed for the earthquake, but this is for before the earthquake. So the Japanese islands are deforming, affected by the compression from these subducting plates. And the earthquake occurred here, and the main shock occurred right about 150 kilometers east of Tohoku area. And 30 minutes later, the biggest aftershock occurred in the southern end of the hypocentral region. So we tried to analyze the GPS data, as Professor Koketsu already showed you, but I think that we made a data analysis independently. And we segregated the effect, the crustal deformation due to the main shock and the largest aftershock. So first of all, I'll show you the crustal deformation observed only for the co-seismic time, and that showed more than 5 meters of horizontal offsets at the tip of the Ojika Peninsula. And also, there was a big subsidence of more than 1 meter along the coast of Tohoku. And this is the crustal deformation, co-seismic crustal deformation observed for the largest aftershock. And you should note that the scale of these arrows are very different. One order of magnitude smaller, and the crustal deformation is, say, something like 20 or 30 centimeters at most. But still, the magnitude of this earthquake was nearly a magnitude 8, so that it is very devastating, and it's much closer to Tokyo metropolitan area. So even in the Tokyo metropolitan area suffered from this earthquake. And this is the results of geodetic inversion, and we found that the maximum offset is something like 20 meters for the main shock. And for the largest aftershock, the slip is about 1 or 2 meters. So you should note that the color scale is 1 order of magnitude difference. But anyway, it seems to me that our result would be a little bit smaller than what we expected from seismological or tsunami data. And our result shows that the equivalent moment magnitude could be 8.7, and it is not 9. So maybe our result is still very preliminary, and we should elaborate of modeling from this GPS data. These are some sample examples of the geodetic inversion from other institutions, and most of them show a very similar pattern, but still, because they are independently analyzing data, and also they use some different geometry of subducting plate. Especially the depth of plate would affect the results, so that we should think more about the geodetic inversion modeling. And if you compare the co-seismic displacement with the before the earthquake, there was interseismic deformation, and there was some research on how the plate coupling is going. And one of the results published by Su and others showed that this area was pretty much coupled, and as the Pacific plate subducts with about 9 centimeters a year, and inversion analysis showed that the maximum coupling could be up to nearly 10 centimeters a year. So we could say that this large area have been coupled mostly in 100%, so that this big asperity may have ruptured by this earthquake. However, as Professor Sato indicated, this earthquake is still not enough to recover for the long-term geologic crustal deformation. Now, I could just very briefly compare with geodetic modeling and seismic modeling. And this is provided by Kokets, but this could be a little bit old version. But anyway, as you may already know from Professor Kokets' talk, that those models suggest a little bit bigger slip, which is a little bit far away from the coast relative to our modeling of using crustal deformation. So maybe we should elaborate the model a little more in the coming days. Now I'm going to the tsunami. Okay. In Japanese islands, we have a number of techniques to observe the sea surface height change. And here we have 3 types of the records. The one is tide gauge records that is located along the coast, and many of near field stations were washed away, and some of them lost the very important part of tsunami. But other techniques like ocean bottom pressure sensor, which Professor Kokets already showed you, survived, which are located about 30 or 50 kilometers east of the coast, and that provides us a very important data. And also, we have so-called GPS buoys, which is a rather new technique that we have developed for more than 10 years. And fortunately, these measuring techniques were established in a couple of years ago along this coast. So these GPS buoys have already provided us the record of tsunamis. And of course, it's very important to make field surveys after the earthquake, and it's still currently underway. So we have not yet obtained any conclusive results, but I just watched the media, and through media, they provide some records. And they mostly show that the wave height inundated or run-up showed more than 10 meters of tsunamis along the coast. And our team from ERI found that more than 30 meters, about 38 meters of tsunami height was observed in the Miyako city. So I just show you some of the results, records that was observed. One is tide gauge records, and as you see, the record stopped at in the midway to the first peak of the tsunamis, and those stations are washed away. So. But still, we show some upheaval record in the beginning of the tsunamis. On the other hand, the GPS buoys here and here show the longer records that clearly shows the first arrival, which shows very peaky large waves that went over 6 meters. Which is this GPS buoy is located about 10 or 15 kilometers from the coast. So as you know, if the tsunami goes closer to the coast, it is exaggerated because of the shallower depths of the water. So it is very consistent that the observed field tsunami height in the field survey is consistent with this offshore tsunami records. And also the ocean bottom pressure sensors showed about 4 or 5 meters tsunami height. 5, 3, okay. Okay, this was already shown by Professor Kokets, and Professor Satake and his team made analysis of this tsunami record. And this is that data, but just I skipped this. And this is results of modeling, and this shows that the result shows that a very big displacement along the fault occurred very closer to the trench, very shallow part of the subduction. And so this is also inconsistent with the geodetic modeling. And this is just observed and estimated tsunami waves. And this, from this modeling, they suggested that the crustal deformation or vertical crustal deformation at the seafloor shows that upheaval of this area is nearly 5 meters. And it seems that this area has generated that peaky, very high tsunami. And this is a picture in case that only this area slipped by the earthquake, and still this created a similar peaky wavelet like tsunami, and that could explain why this very large tsunami occurred by this earthquake. So finally, I'd like to just touch on the tectonic implications, but the one thing is that why did the coast of the Sanriku subsided rather than uplift to reconcile the long-term uplift of the in the Quaternary age? So we have to think about that. What kind of mechanism is working here? The very simple thoughts of the geodetic subsidence before the earthquake should be due to the drag of the oceanic plate to the continental plate, and that could be rebound due to the large interplate earthquake. But the truth was not. And if you compare, this is already told by Sato, that the quaternary uplift and the geodetic, the subsidence should be reconciled somehow. This was already showed. And so there are a number of mechanisms you could hypothesize, but one thing I could suggest is that a large post-seismic uplift could occur if the slow slip goes down at the downward extension of the fault. If we assume that there is a displacement of 2.5 meter in the depth range of 40 to 90 kilometer, could uplift the cost of the equivalent amount of the subsidence that was created by the earthquake. So this is a summary, but this is just a repetition, so I just skip it. Thank you very much.
Okay, we have time for a short question or comment. Okay. Let's go over here.
Thank you very much for the nice talk. Since you are the last Japanese speaker, first I want to ask why there is no talk about the foreshock 2 days before? Because there had been a very, very important clue if we look at the rupture process of that. And the second question is that, do you have any assumption about the nature of the 7.9 aftershock that happened 30 minutes after the moon? Isn't it a subducted seamount?
Oh, okay. Sorry, I didn't understand your first question.
Why there is no talk about the foreshock on the 9th of March? Because
you're asking about the foreshock?
Yes.
Okay.
Can you speak into the mic?
Yeah.
No, you've got the mic. Okay, sorry.
Well, as for the foreshocks, actually, there was a very active foreshock sequence that started March 9, and more than magnitude 7 earthquake have occurred. So at that time, we didn't recognize that is a foreshock of this earthquake, but finally, that was a precursory earthquake. And another thing, about the southern end structure, that this is not my own data, but someone tells that at that time, as I showed you, that the tectonic environment is very complicated. One is Pacific plate is subducting, and from this side, the Philippine Sea plate is subducting. And that is colliding just at the place of the southern end of this large earthquake. And that is where the largest aftershock occurred. So someone speculates that their further seismic activity may extend further south beyond this very special circumstance. Am I answering your question?
Yeah, I think any extension discussion we're going to need to leave for the panel discussion on this, but thank you very much. Okay.
So let's go to the next speaker. So the next two speakers will be talking about tsunami in the intermediate field. The first of this speaker, it's Michael Nosov, and the title is Tohoku Tsunami Impact on the Russian Coasts. Then we will go to the Pacific Ocean.
Good morning, and thank you to conveners for the opportunity to give this talk. Oh. It doesn't work. No.
Just a sec. It's just being recognized by the computer.
Okay. Okay, so I'd like to introduce myself, Mikhail Nosov, and my co-author, Tatiana Velskaya. She is the chief of Sakhalin Tsunami Warning Center, Federal Service of Russia for Hydrometeorology and Environmental Monitoring. I'd like to say that after this event, I also became partly Japanese, because during the earthquake I was just in this twinkling point in Kamakura and felt it myself. And Kamakura is a nice place, an ancient capital of Japan, and just the moment of earthquake you can see on this animation. The shaking was not so strong, but you can see that trees are slightly shaken, but no wind at all. So after it, let's go down to business. And my first slide is Tsunami Bulletin, which was issued by Pacific Tsunami Warning Center in 9 minutes after the earthquake. And you can see that, of course, the first tsunami warning was issued for Japan, and the second number is Russia. And I think this is why my talk is here. I have, after all these frustrating images all of you watch on TV, I have a few good news for you. And in Russia, we have no victims, we have no considerable property damage, and Russian Tsunami Warning Service successfully passed this exam. First of all, I'd like to show a table of action of Sakhalin Tsunami Warning Service. So a 0 moment corresponds to the earthquake, and in 2 minutes after the earthquake, it was recorded by Yuzhno-Sakhalin seismological station, and in 3 minutes we have tsunami warning issued for Japan from GMA, and in 12 minutes tsunami warning was issued for all the Kuril Islands. And in 13 minutes we have tsunami bulletin from the Pacific Tsunami Warning Center. So tsunami warning was issued in Russia based only on the data of Russian Seismocenter. And after it, alert system for the Kuril Islands was started, so sirens, TV, and megaphones, and population was evacuated, and vessels put to sea. And in 17 minutes, tsunami warning was disseminated to departments of Federal Service of Russia for hydrometeorology and environmental monitoring in different regions, Kamchatka, Primorye, Khabarovsk, and even to Moscow, just for information, of course. And in 18 minutes, tsunami warning was transmitted to foreign tsunami centers. After it, analysis of seismic of sea level data and tsunami manifestations on the Russian coast was performed. And on March 12 at 2:20, Sakhalin Tsunami Warning Service canceled the tsunami warning. Here's the net of sea level gauges of Russian tsunami warning system, And you see here 23 stations, 23 digital stations, and all of you can access to the data using this site. Unfortunately, the site at the moment is in Russian, but actually you can go to the third point inside, and the interface is rather friendly, and it looks like a dark noir interface, so I think you can extract data if you like easily. Anyway, you can ask me in case. 16 sea-level stations, coastal stations, recorded the Tohoku tsunami in Russia. And all of the stations are shown on this slide. And next, I'd like to show you all the records. I will show records of the duration of 2 days, so 48 hours. And the first one is record at Yuzhno-Kurilsk, and you see the double amplitude was a bit more than 2 meters. The next station, Kurilsk, double amplitude was only 58 centimeters, which is much less. And the reason is that Kurilsk faced to Okhotsk Sea and Yuzhno-Kurilsk faced to Pacific. The next point, Korsakov, port of Sakhalin, and here you can see that double amplitude was 65 centimeters. Next point, Cape Krelyon, 33 centimeters, Starodubskaya, Sakhalin also 63 centimeters, Paranaisk, 81 centimeters, Nikolskaya on Bering Island, amplitude, double amplitude 24 centimeters. And Semyachik, double amplitude, a bit more than 1 meter. And here we have 1 hour when the station was out of operations. This is why the first part of the record is from 0 until 10 hours. And this part of record from 12 hours till the end. And here we have double amplitude 1.28 meters. Petropavlovsk-Kamchatsky, 25 centimeters, and the reason for it that tide gauge is established inside the bay. Tatarsky Strait between Sakhalin and the main city Uglegorsk, double amplitude 20 centimeters. Holmsk, port of Sakhalin, also 26 centimeters. Nevelsk, 27 centimeters, and then Rudная Пристань, 37, Преображение, also 37, Nakhodka, 36, and Vladivostok, 22 centimeters. And finalizing this picture, I'd like to show you that, of course, the closest area, South Kuril Islands, has maximum amplitude up to 3 meters, and the 3 meter is visual estimate for Malokurilskaya Bay, which is situated on Shikotan Island. Also, we have some visual estimate for Magadan, which is beyond of this map, somewhere to at the north of Okhotskaya Sea, and visual estimate is 1 meter. And also we have visual estimate for the Severokurilsk, which is on Paramushir Island, and visual estimate 2.5 meter. Also, we have a Russian DART station, which was established, as I said, just before the event. It was established in August of 2010, and it successfully recorded Tohoku tsunami. And you see that double amplitude is 0.92 meters, which is rather large value for the deep ocean measurements. And the neighbor station, DART station, the closest to the Tohoku tsunami source, recorded 2.8 meters double amplitude, which is the huge value. This is, I think, that the first record have ever been obtained of such amplitude for the DART. And the other neighbor is the station, which to the north of Russian station. The amplitude is rather modest, but this slide is just to show you how the DART recorded tsunami in advance to the coastal tide gauge. You see that we have time gap of 36 minutes before the arrival in the coastal to the coastal tide gauge. And as for the Russian station, which is a bit to the south, we have time gap 60 minutes. So it means that installation of the Russian DART station is very useful for defense of southern Kuril Islands. So 60 minutes, that's enough to perform some evacuation. And the next few slides, I'd like to show you photos, some photos which were taken by people from Kuril Islands. It's Yuzhno-Kurilsk. You see that ships are put into sea. Photo by Andrei Gritsenko. The next photo by Dmitry Vasilyev, Malokurilskaya, which is situated on Shikotan Island. And in this place, you see that a lot of blocks of ice and run-up at this point was up to 3 meters. Also, Shikotan Island, Krabovaya Bay, in this point, run-up was also up to 3 meters, photo by Oleg Volkov. Again, Yuzhno-Kurilsk, the second wave is approaching. Photo by Andrei Gritsenko. And the last one, Severokurilsk on Paramushir, you see that some traces of tsunami on the snow, and run-up at this point was up to 2.5 meters. And in what follow, I'd like to show you some numerical simulations. And here is the bottom deformations due to Tohoku tsunami, which was calculated in my group using USGS finite fold. This is the first estimation of USGS, and you see that horizontal deformation, which is shown by green arrows, was up to 8.5 meters, subsidence up to 1.4 meters, and uplift 5.5 meters. But this is only the first estimate, and after it, USGS issued the second estimate, which is which gives the following value after calculating in bottom deformation. So we have horizontal displacement more than 17 meters, subsidence up to 2 meters, and uplift, maximum uplift, up to 8.9 meters. We recalculate this horizontal and vertical deformation and bathymetry in the vicinity of the tsunami source. We recalculated in initial elevation on the surface. After it, we apply to this initial elevation smoothing technique, which delete from this initial elevation short components which are not peculiar to any disturbance of the surface, which can be generated by bottom deformation, and obtain the following smoothed initial elevation. And we, using shallow water code, perform numerical simulation of this event. And next few slides to compare DART measurements, which are shown here by black line, and synthetic mariograms shown by red line. And you see that for the Russian tide gauge DART, the amplitude corresponds quite well, actually. But the small time gap between these two peaks, I think, can be explained that we pose the initial elevation just at the beginning of the earthquake, but the earthquake runs for a couple of minutes or even more, and this is why actually this peak can be shifted. The next DART station close to the source also you can see that rather good coincidence of amplitude. The closest to the Tohoku source, here we slightly underestimate tsunami amplitude, and the next station also we have rather good coincidence. So if you have such pretty good coincidence measurement of and numerical calculations, so you can trust to the following picture, which show maximum amplitude due to Tohoku tsunami in logarithmic scale. And actually, you see that these calculations are in a good agreement with measurements. As for Japan, no doubt that on this coast you have amplitude more than 10 meters. As for the southern Kuril, few meters can be, and on Shkotan probably the largest. Sakhalin, you see that approximately more than 1 meter, less than 1 meter. Paranaisk also near the 1 meter. And here in Tatarsky Strait and Japan Sea, amplitude less than 1 meter. So instead of a conclusion, I'd like to repeat again that in Russia, fortunately, we have no victims, no considerable property damage, and Russian tsunami warning system successfully passed the exam. So thank you for your attention. That's all.
Thank you very much, Michael. Questions? So may I ask you a question concerning tsunami? Ah, sorry, please.
Okay, I have maybe stupid question, but on the dart pictures, if you show any of your dart pictures, before the signal, you have a very strong high frequency signal in the first part. Can you comment on it?
Oh, of course, it's a seismic wave, relay seismic wave, which uplifted bottom and thus provocates pressure variations.
Okay, but can you do some estimations based on these measurements? Not by the time.
I think yes.
Yeah.
I think yes. We can do this estimation, but it's not for now. It has not been done yet. By me, probably somebody else.
Emil? Just a minute, the microphone comes.
These Israeli waves, which are recorded by the DART station, they are undersampled, usually. I don't know what your sampling is, but on the classical US DART buoys, you cannot really use them too well because they are not sampled properly.
Yeah, you're right. The sampling interval approximately 15 seconds. Here it's not enough. It's not enough here.
Other questions? So if not, I've got a question concerning the inversion of the tsunami data. Or I don't know, your sleep model was deduced from tsunami data? Was that deduced from GPS data? From what? I didn't understand that. Then I put the question. So it seems that your solution is a bit different from the solution that was provided before by the Japanese colleagues. So usually the slip is much less. And even though you are able to reproduce DART buoys quite well in the size. So do you have a comment on that?
No, the maximum sleep, I used USGS finite fault. The maximum sleep, if I remember correctly, I think 33 meters. 33 meters. So it's in good correspondence with Japanese colleague.
Okay, thank you. Other questions? If no, we move to the next speaker. Thank you, Michael. Next speaker is Emil Okal, and he will talk about the tsunami propagation in the Pacific Ocean. The title is Lessons from Sendai, a Perspective from Polynesia and the World.
Well, thank you very much for inviting me for this, in this session. I would like to provide a perspective not only from Polynesia, where I happened to be during the tsunami, but also give you a number of very preliminary scientific results.
I think we should keep some lessons from this earthquake, and the one lesson to take home is a lesson of humility, as I will show. The earthquake, as you all know, has a classical subduction geometry. It is not a surprise to the community of geophysicists who've been studying and teaching plate tectonics for 30 or 40 years now. It is big, and it did surprise us with its size. It's the fourth largest event ever recorded for which a documented verified seismic moment is available. Now, why did it surprise us? It's because megaquakes, which reach magnitude 9, were generally unknown in all subduction zones, which in an area which may reach in some areas of the trough about 140 million years. And also, megaquakes were generally unknown in relatively poorly unsedimented areas. And so several models, several paradigms of the expectability of these mega events have to be abandoned now, as I will show you. The first one is, of course, the very seminal and very smart model which was proposed in the 80s by Raff and Kanamori, which correlated the age of a plate and the rate of subsidence of a collision with the expectable maximum earthquake. This is something that I had been teaching for 30 years, and I'm afraid I don't know what to teach next quarter in my class, because we'll have to find a better mousetrap in a sense. As you can see here on the diagram, the Northeast Japan was expected to have a maximum magnitude of about 8.2 on this diagram, and it was about 8.9 or 9.0. In this respect, it is quite similar to the Sumatra event of 2004, which was listed here, also at a maximum value of about 8.2, and as you know, was much, much larger. So once again, we have a lesson of humility here that we need to take home, which is we do not understand something which we thought we understood before this earthquake, and to some extent also the Sumatra earthquake. Another model was proposed, notably by David Scholl of the USGS, whose picture is here, and which expressed that that megaquakes here occurred only in those areas where you have very thick sedimentary layering, which was understood to mean that these sediments provided a gluing which led to a stronger coupling. Unfortunately, over the past years and so, I had become involved in reassessing some of these earthquakes here, which occurred in poorly sedimented areas, and I had moved some of them to the right, which meant that the model was becoming questionable. And of course, the Japanese case here moves the maximum known magnitude from about 8.2, 8.3 to 9.0, and this is one more event which betrays this model, and at this point, it is impossible to salvage this idea. And actually, Dave Scholl very graciously sent me an email in a few days, and he said, I give up. And so, one more thing that I can no longer teach. So we have to take a precautionary approach, and we have to say that we should consider that all long subduction zones which are more than maybe 400 kilometers or 500 kilometers in length, are potentially megagenic. They may produce very large earthquakes in the future. And in particular, this holds for places like Tonga, Camargue, the Marianas, Java, East Luzon, the Caribbean, the Solomon Islands, and so on, where we should have revised vigilance. This being said, I want to move now to my personal perspective on this event and my personal experience. I was on a research visit to the Laboratory of Geophysics in Tahiti here, 9,500 kilometers from the epicenter, which means that the tsunami travel time is about 11 and a half hours. And I was able to witness and assist my friends, Dominique Raymond and Olivier Verneau, who are in charge of the laboratory and who delivered the alert for Polynesia. So I want to go through something very reminiscent of what Mikhail Nosov just showed us, which is the timeline of the tsunami watch in Tahiti. The earthquake occurred at 1946 local time in the evening, and the automatic alarm rang at 1957. By about 20:30 here, I returned from dinner to the lab, and we had by then the news that of course the estimate was about 8.8, and we started by simulation of the tsunami, and we obtained a prediction based on some unpublished, yet still unpublished work that I had been working on with Dominique Raymond at the time, and we predicted an amplitude of about 40 meters in the harbor at Papeete. That means in an area which does not enhance the tsunami too much. By about 2145, we had all quasi-real-time characteristics obtained, such as energy to moment ratio, duration of P waves, and so on, which I will show a little bit later. And then we had the luxury of time, because we were so far away. It was about 2200, and we knew that the waves were expected at 7 o'clock in the morning the next day. So we had a very, very long night when we knew what was going to happen, and we were just slowly getting reports from the dart buoys, from the maregraphs in the intervening islands, and so on. By about 2300, there was a statement from the governor's office which alerted the population that there may be a tsunami alert. And by 0100, we had a red alert, which meant that all the civil defense people were put on standby. There is absolutely no need to wake up the population at midnight to have them spend the whole night when the waves come only at 7 o'clock. And this is why the evacuation order was given only at 0430. 147 sirens on 68 islands in French Polynesia wailed. And the first waves reached the first island at Mopiti at 6:30, and then in Papeete harbor, 20 centimeters on the port maregraph, which was about half, no, this was about half of what we had computed. That's going to be very interesting. The first waves reached the Marquesas at 0744 Tahiti time, which was 0814 in the Marquesas, and they reached 3.5 meters over there. By 0832, we had a decreasing wave height in the harbor, and so that suggested an all clear. There was a great deal of pressure from the political side. They were calling us and asking us, you know, can you issue an all clear? And we said tentatively yes. By 0844, the alert was reinstated because the waves then reached 38 centimeters in the port and 2.5 meters, 15 kilometers away. So there is a lesson there which I will come back to, which is the biggest wave rarely is the first one. The final all clear was sounded everywhere except the Marquesas at 0930. By 10 o'clock the airport reopened, and at 12:27 it was the all clear in the Marquesas, so that finally we could go to sleep after a 31-hour day. What are the lessons? Pretty much like Dr. Nossoff told us, this was a success. A great success. There was an orderly evacuation, no casualties, no boats lost, a few houses washed in the Marquesas, but there was some damage to hangars and fishing wharfs on the beaches of the Marquesas. This is unescapable. One very close call for a not-so-smart resident, careless resident who went to pick up dead fish on the exposed seafloor, which is something you should never do. And there is the question of this alert, which was cancelled and then immediately reinstated. There is a message to take home also. The largest wave is rarely the first or even second one. And I don't think that we have a clear theoretical explanation of why this is the case. This is a case in point which was published in the newspaper the next day. This is a maregraph at Papeete here, and you can see that the first two waves are about 20 centimeters in height, and that the third one is essentially double the amplitude, which led to this cancellation of the alert and immediate reinstatement of the alert. So this is a point in case to remember. The third wave or the fourth wave may be the largest one. And look at the scale here. They are separated by something like an hour and a half, which means it's a long time. And it's very difficult to instill in people the need to stay away from the beach on this alert. From the newspaper the next day, you see the people driving their cars or parking their cars out of harm's way here. It all went very well. It says in French, a calm population. Things went really very well. In the Marquesas, this is where in Taipivai, the wave penetrated in an extremely indented valley. The wave penetrated approximately 500 meters inland and did substantial damage to this to this construction which is used to dry copra on the beach there. Let's go back to science a little bit. During that long night, we did a number of very quick and dirty measurements to get a good feeling on the event. First, the ultra-long period mental magnitude, and you see that the mental magnitude here creeps up and then sort of levels off at a frequency of approximately 4 millihertz, which indicates that there is a corner frequency in the spectrum there, which probably relates to a duration of approximately 100 seconds for the source. The next thing we did was to look at whether the earthquake had any slowness. And no, it doesn't exhibit any slowness. It's not one of those tsunami earthquakes that Kanamori has defined. The theta parameter is typical of what we obtain for our subduction zone events. And similarly, we looked at things such as the duration of high-frequency seismic wave, the duration of high-frequency P waves, which is actually somewhat shorter than expected for an earthquake of that size. And the reason for that is, of course, that it's a bilateral rupture, so essentially the duration is divided by 2. Duration versus estimated energy, which is also a parameter which will tell you if the earthquake is anomalously slow. Anything which is above the red dot, like this here, is, anything which is about the red dot would be a kind of tsunami earthquake such as Nicaragua in 1992, and you see that the 2001 doesn't qualify. It doesn't have an excessively long duration for its estimated energy. So all in all, it's pretty much a textbook earthquake, except it's very, very big, but there is nothing anomalous in its spectrum. This is something that we wanted to investigate a little bit later, but you have to be patient if you want to study the Earth's normal modes, because you have to give them enough time so that they can ring long enough, that you can sample them long enough. So you need at least 2 weeks of data, perhaps 3 weeks. And these are the spectacular spectra that we get of the splitting of 0s2, in this case, the gravest mode of the Earth, recorded at Canberra in Australia, and by fitting the theoretical seismogram on this, and in this I was aided by Seth Stein, you can derive the moment, and you see that the moment which is derived here is very close to the moment obtained by the W phase inversion, even though this is taken at 3,000 seconds. So it means that there is no very slow component in the seismic frequency range. There is no very slow component to that earthquake. So as of the 1st of April, which is when I made this, figure here, we had processed 103 spectral amplitudes of split normal modes, considering 7 modes, and the moment all the way from about 600 seconds to about 3,200 seconds, and the moment is remarkably flat. In the case of Sumatra, you may remember that these pictures would show a moment which was growing with period here. This is not the case. The moment is flat. This is a textbook earthquake. The value of a static moment is about 3.6 times 10 to the 29, so it's actually a little bit lower than the W phase inversion of the USGS, which is here. I'm not sure that the difference is significant, but it goes towards this reported slight deficiency in seismic moment from the tsunami inversions that were described in the previous talk. So there is another question that we don't, in all humility, that we don't understand here, which is, which are these earthquakes which are really slow, which have a spectrum which keeps growing at very long periods, such as Chile 1960, Sumatra 2004, probably Alaska 1964, for which Meredith Nettles has shown that the very long period inversion is somewhat bigger than proposed by Kanamori in 70. And also the Rat Island of 65 probably shares this characteristic, as opposed to earthquakes which are just about as big here, but not slow, such as Nias in 2005, Chile in 2010, and now the Sendai earthquake in 2011. Big question mark. This is a subject for further research. And now, finally, I want to go to an even greater distance, and I want to tell you what the tsunami did at the other end of the Pacific Ocean, in Antarctica. And this is something that Kelly Brandt has been working on with a little bit of collaboration on my part. We have here satellite pictures of the Sulzberger ice shelf, which is somewhere there in East Antarctica over there, taken at intervals which are not exactly regular, but somewhere on the order of once or twice a day. And you see that you have a piece of ice shelf here, which is solidly attached to the ice shelf. On the next picture, these are these two pictures over there. On the next picture, you see that clearly it has rifted away, and it leads to the carving, and it leads to the decomposition of that piece of ice shelf over a period of a few days here. But unfortunately, this is Murphy's law in a sense. The sampling that we have in terms of pictures here is probably the longest interval is when the tsunami arrives. But still, you can see that as of this particular time here, which was something like 1200 GMT time on the 11th, this is after the earthquake, certainly after the seismic waves. You still have the unbroken part of the ice shelf. And the next picture we have here, which is about 1 day later, the ice shelf is starting to carve. And the projected arrival time of the tsunami is 23:15 UTC here in between. So there is every reason, and by the way, this thing had been stable for 45 years before this particular event. So there is every reason to believe that the carving of this part of the Sulzberger ice shelf was triggered by the tsunami when it hit Antarctica, and it gives some support to an old observation of the Chilean Navy in 1868 following the Arica tsunami, the major Arica tsunami. They reported that they had found an unseasonably large number of icebergs in the southern oceans, which they didn't know why they were so many, and that they had fragmented shapes and so on, and it was speculated that it had something to do with the Arica tsunami. So this observation here is in support of this possible effect of very large tsunamis on Antarctic ice shelves. Thank you very much.
We have time for a couple of short questions or comments. Okay, yeah, John?
Emile, your comments that the first wave is very seldom the highest, we've looked at some hundreds of simulations in the near field for Sumatra, and the first wave is almost always the highest. Is this just a near field effect, or is there something, do you think, different for the bathymetric geometry there that changes things?
I'm in the process of gathering hundreds of records of teleseismic marograms and so on. And I think it's probably something which has to do with propagation, because as you say, in the near field, the highest is oftentimes the first or second one. And we have countless examples. Crescent City in 1964 is a particularly tragic case. Hilo in 1960 is another very tragic case where people see the first wave and they say, hey, this is over, and the next one is much bigger. So yes, it probably has something to do with propagation. We have to try to figure out if it's rooted in bathymetry, if it's rooted in mechanism, directivity. Does it depend on the azimuth? Does it depend on distance? Does it depend on the influence of bathymetry? There is a large amount of work to do, and I think we're going to have to depend on simulations, because we just don't have enough good data to separate all these parameters. But it's the lesson. Tsunamis, we have to remember that tsunamis are not a hazard which is limited to coastal nations, because we travel so much. And so it's a lesson that we should have. And when I say we, I say the entire world community. We may be on vacation. Sweden had its worst disaster during the 2004 tsunami. We may be on vacation, and we should remember always that the arrival time of the first wave may not be the time of the maximum risk. It's a very important message.
Okay, thank you very much. I think we'll be moving on to the last talk of this session, and this will be on the financial aspects of the event itself, and it will be given by Gero Michael, and this will be changes in risk and reinsurance risk perception after the Tohoku earthquake.
So this is forward? No, which one is forward? This one. Okay. Does it not work? Sorry. So it's a pleasure to be here. Did I do something wrong? No, it's too forward. Oh, there it is. So which one is forward? Oh, this one. Okay. It's a pleasure to be here, and I would like to open up another window to somewhat different thinking very often, because we are, in our market, not necessarily specialists. So it's the insurance and reinsurance market. I stand here for a private-public partnership of quite a number of scientific institutions and the insurance world, where we actually aim at bringing science and understanding to the industry, and then, of course, the thinking of the industry to science to interact further. One of these partners of us, it's the CDM group, and it's James Danielle has very quickly after the bigger earthquake in Tohoku done a lot of modeling, and he came up, and actually numbers are going up over time simply because he includes business interruptions, and he comes currently to an economic loss in the order of $320 billion US, and the number of fatalities in his modeling is sitting roughly in the order of 27,500 people. That includes, by the way, the tsunami as well. So quite a number of questions here. How large is the insured loss? Why is that loss eventually very different to the economic loss? How did companies react? How well did our models really work in an end? And has this event changed the near field and around the globe, and especially the ideas of, I say later on in our market, there are very interesting ideas, what they call the ring of fire. Okay, if I look into losses around here, I've just mentioned it, there is in the order of 300 billion on the model, before said in the order of 320 billion. The Japanese government is currently, I think, roughly at 309. If you look into the insured loss, Applied Insurance Research is one of the vendors in our market. They came up with an insured loss of only 15 to 35 billion. Reinsurance, so there's an insurance and a reinsurance part. The insurance part is probably only between 10 and 15 billion. And then a comparison to a few other earthquakes, or a few other events recently, and you see the deep water horizon, the Chile earthquake, or the Christchurch earthquakes, which come relatively high. There's another event there, you might not know it all, which is the model change event of one vendor. We don't know how large that event is, but it's probably very large. Okay, if we look then into some insured losses around, there are some limited numbers, but our current estimate with all what we have from both Japanese clients as well as international clients, we see in the order of 20 billion insured loss. Now, if you look then at the rating agencies, these are essentially companies that rate whether insurance and reinsurance or the banking side is still viable, whether they still have enough capital after a big event, or they look also and rate companies according to their credit rating and end. And so they looked into the earthquake and said, it's probably not a major issue, actually, for the insurance and reinsurance world. Now, loss perception. As you all know, most of the companies are listed companies. They're in different stock exchanges. And what you see first in blue here is how the S&P 500 reacted. And it's interesting that the 11th of March is part of a larger kind of a downturn you see there. So there's in the order of 37 3.7%, but then it was a very quick rebound. So the overall world doesn't necessarily believe that this is really endangering a lot of companies. Now on the right side, you see how that between 4th and 11th, on 18th actually of March, quite a number of companies, don't worry that you can't read it too much, but there are huge differences. And we come to percentages of equity loss according to the share price difference of up to over 20%, which is quite substantial in this case. It's interesting that this expectation of loss, because it's only the international, it's only 50%, it's probably much higher than it was really. And one of the reasons for that might be, A, because it's anyway in a large downturn, but then also that the difference between the insurance and the economic loss is so large. And there you see it again. So on the left side, you see these huge difference in economic and insurance loss. And that's the case actually for a number of areas in the world. And in Japan, there's probably more than one reason for that. One reason is that in the past, Japanese insurance companies thought that earthquake is actually uninsurable. And the reason for that is, uninsurable here means it's adverse selection, because we know it will happen. You can't really hide it in many ways, and the loss might be so gigantic. We're talking about eventually $1.5 trillion US in a large Tokyo earthquake, that this will devastate companies. It will not work. You will never get the premium for that. And so that companies in Japan often thought it's uninsurable. In order to overcome a bit that, or square that circle, they have created policies which we call first loss policies, and you see that on the right here. So there's a huge potentially to insure, TIV, total insured value. But in action, what is really insured is only a very, very small limit, and that limit for individual companies might be only in the order of 1 or 2%. And that makes, of course, a large difference. Well, what really made the loss here was not the big companies, it was not the commercial industrial, it was the homeowners. And there's a pool for homeowners in Japan, and most of the loss there goes into the government pool. Reinsurance doesn't even see that. But in addition, there are a lot of cooperatives, and these cooperatives have really the largest loss. Most of the loss, by the way, was clearly done by the tsunami, as you probably all know. Okay, the very interesting thing for that earthquake was also that it fell exactly in the time of policy renewal, so of the period where the contracts of the reinsurers with the reinsurers, insurers with the reinsurers are renewed. And the windstorm contracts had almost been done, and then the earthquake contracts are normally coming, and there was the earthquake. So there was first a lot of uncertainty. What is going to happen? Can we even reinstate or renew these contracts? And prices went up quite significantly. So the prices for earthquake at average went up between 20 and 70%. Even the windstorm rates went up, although they, of course, didn't have a loss. And there were certain layered deals which had a lot of the earthquake risk in there, and they were extended by another 3 months. But after a first kind of a challenging time, everything ran relatively smoothly, so the international community has bought into that relatively quickly. And you've seen the figure from Suva already. I mean, it's an earthquake that's larger than all our models, but nonetheless, there were probably a few indications in the past that, or in some of the science, that probably might have pointed to the fact that there might be a possibility of a very large event. Nonetheless, it was unexpected. It's another black swan out of many, many, many black swans we have. There's another very interesting thinking in our market. And you as scientists think very different, I know. But for the market, it's different. What they see is Chile earthquake and the big loss. Then they see the New Zealand earthquake. It was only magnitude 6.3, but they see it because it was a loss. And then, of course, they see the Japanese earthquake, and then they say it's the next one sitting in California. And this came then into the press, and the press changed it. They called it the Ring of Fire, and it's all very strange in many ways. But these are the questions. The most questions I get nowadays is exactly that. Is the next earthquake the earthquake in California? And we know, of course, magnitude 6 earthquakes happen the order of every 3 days. Another very interesting thing is that in Germany, the reaction there, they had an election there, and the Green Party was getting an avalanche of votes. Because these people stand, of course, for shutting down the nuclear power stations. And so although the risk hasn't changed in Germany, that risk which sits there somewhere, or the loss that sits at the other end of the world, has influenced politics in Germany quite significantly. Another thing in our models, and we use the yellow, or the model on the right there, and if you look, compare that to the Earth, so what you see essentially is the likelihood of earthquakes and where the earthquakes really happened. And it's interesting, where the highest likelihoods are, according to these more what we call time-dependent models, they were not the largest number of earthquakes. And surely the big earthquake didn't happen there. We did, on the left side, a very quick check with the Gutenberg-Richter approach. It's just per perfection. It looks a bit better. But the challenge is really that our models didn't include neither the size of the earthquake, nor probably also that there was such a large risk in that area. So in order to address the challenges our different insurance and reinsurance company had about, they look into long-term modeling. Now, they don't really include aftershocks and an end in their models because most of the time they don't create a larger loss. Well, that has changed recently with Christchurch, whether we call it an aftershock or not. And so what we did is very quickly, we did a Monte Carlo simulation. You all know that. It's essentially Omori's law. And we looked into couples of earthquake during the USGS global catalog, and we saw that right at the time of a magnitude 6 or larger earthquake, another magnitude 6 of larger earthquake in the area, smaller than 300 kilometers, is roughly 10 times at average in the world compared to what it is over the longer term. And we all know that, but this is even true if the first earthquake, the second earthquake is the same size or larger, because the first earthquake again could be an aftershock. Now if you go further out, and that was really the question our clients had, if you go further out than 500 kilometers and do the same approach, so the same Monte Carlo sampling of couples of earthquake, there's no correlation whatsoever. So at least for the large earthquakes, 6 and larger, there was recently some work from Ross Stein and his colleagues that showed the same thing. So we don't necessarily expect that this earthquake triggers a magnitude 6 or larger in California. Other work we do is together with Ross Stein and his colleagues, and he allowed me to show these pictures here, and what you see is the redistribution of stresses and strains. So it's interesting that this earthquake, probably for the first time, has triggered a lot of interest in our market in what's now happening to other areas around. Whereas in the past people said, okay, there's an earthquake, the likelihood of another earthquake is very small, because that's what they thought in their old lag time models. We're no longer sure whether this is true. But nonetheless, the question came now up, what's around the area of the earthquake? And he did a tremendous work. The paper is just finished, and I think it's in Earth, Planet and Space or so, they just submitted it to a US and Japanese journal. But what's very interesting for the market here, of course there are a lot of areas where the risk is up, and especially if you go a bit further south of where the earthquake happened, the risk is definitively up. But the Sagami fault, which is the fault of the 1923 earthquake, the worst case scenario in our models, along that fault in that area, the risk actually seems to go down. So what these models now tell us is probably the likelihood of an earthquake along that fault close to Tokyo, so like the 1923, is actually more remote than it was before the earthquake. Now that's true or not is another question, but it's surely a very exciting result from those guys. So, what we conclude, less than 10% of the earthquake is really insured. The share price overreacted initially. Size and impact of an event, was unexpected. We think that's another black swan, like, New Zealand, essentially earthquake, Christchurch was a black swan, Kobe was a black swan, Northwich was a black swan. Most earthquakes that happen and have a very large loss are very close to be a black swan. The Chile probably was not. The regional reinsurance rates were up by up to 70%. We don't necessarily see an obvious Chile triggering of earthquake, as you probably all know, but our industry doesn't. There's a huge, what we call Taylor change of risk perception, and you've seen, you know, in Germany, southwest of Germany, quite a difference in thinking. And the stress redistribution brought, apparently, the Kanto 1923 earthquake fault further away from Rupture. Thanks a lot.
Thank you very much. Questions?
Thank you very much. Regarding your conclusion number one, would you care to comment on whether this figure of 10% would be different geographically? And I'm referring perhaps to California. Could we get a feeling whether the fraction which is insured in California is comparable, bigger, smaller?
It's comparable. And it's all very worrying. But the reason is probably very different. Now, in Japan, the homeowners are very much insured. What is not insured, they might not be paid out the full amount, but there's insurance for them. And there's the government pool, and the government pool seems to actually work very well. There's, I think, in the order of 50, 60 billion US dollars currently in that pool. What is very, very much less insured in Japan is the commercial and industrial business. In California, however, the pool is further shrinking, which essentially means that the premium is going further up, and the deductibles are massively going up. Very different to in Japan. So with these huge deductibles, you know, we have to pay eventually 50, 60,000 for your house before you get even $1 of money from the insurance company. It's something which brings people further away, and the pool shrinks further, and with further shrinking, the price goes up further, and the whole thing is a bit of a challenge. And, you know, there are a lot of ideas how we can change that, but there are other areas in the world where this works probably a bit better, frankly. There's a pool, for instance, in Turkey, which, although penetration is not too high, that pool seems to perform quite well. There's now a new pool in Romania. Had been started some time ago with the World Bank. I think the World Bank is now out of that, but nonetheless, it's also a pool we do administer and work like the Turkish pool. And that seems to gain really interest as well. But premium is very, very small. If you essentially have to pay in the order of 20 to 50 bucks a year, you know, you go there. Even if you don't get too much, that will help after an earthquake tremendously.
Thank you. Other questions?
I wonder how the estimation of unloading in Sagami Bay is reliable. Notably, does it vary with respect to the exact distribution of slip? And what is the influence of the post-seismic, which currently occurs in the southern part?
So you're talking about the Ross-Stein modeling, is that correct?
Yeah, that's how is it sensitive to the slip distribution and to the post-seismic?
Yeah, I think the best, I have a few ideas, but the best is really to contact Ross-Stein on that. He has included, I think it's purely elastic, he has included the largest aftershock in the south, but that's essentially what it is. He's done a lot of remodeling and reconstraining with a number of different results, but he is the best to go for and discuss with him.
On the issue of how much insured loss there would be for a future destructive earthquake, is the percentage different in Tokyo? I know most of the world's insurance and reinsurance money is tied up in Tokyo. If a big earthquake occurred there, would the percentage of insured loss be as low as 10%, or would it be greater?
Overall insured in Japan, and that is related to Tokyo if you want, is currently in the order of 100 billion only. Roughly half of that is in the pool, in homeowners pool, and roughly half is in the insurance reinsurance. It's actually not probably fully correct that most, if you look into, our market is currently capable of covering between 300 and 400 billion US dollars, and most of that sits definitively fine in the US. There's no question. The biggest events that the market will pay is in the US. I think where the numbers come from, that it's not necessarily the insurance market. If you look into, if we have a 1 trillion, 1.5 trillion economic loss, where will the money come from? And what we already see now with that earthquake, a lot of money comes from foreign areas, because it's essentially the Japanese take out the money, for instance, from the US eventually and from other areas in order to pull back. And that is, of course, there are quite a number of scenarios people have calculated through what that would mean for the world economy, a very large earthquake, and we can all speculate on that. But yeah, for insurance, as said, it's just 100 billion.
Thank you. A last question there.
I know that the stress interaction analysis that you talk about for the Tsunami fault has been put to really good use in trying to understand the seismic hazard around Istanbul. Do you have any idea of what the effect that has been on insurance premiums in Istanbul? And could you comment on whether you think that's a positive effect or a negative effect for the people living there and the scientists who are doing this type of work?
So are you talking about whether this Japanese earthquake has an effect on the insurance in Turkey?
No.
Or the Turkey earthquake on Turkey?
Ross Steins, among other people, have calculated Coulomb stress changes on the faults around Istanbul.
Yeah.
I would like to know, do you know anything about the change in insurance premiums there as a result of that forecast? And do you think this is a positive thing or a negative thing for poor people in Istanbul?
Yeah. Okay. I mean, especially this propagation of deformation from east to west and all what comes with that has been included in the insurance and reinsurance models. And with that, of course, the likelihood of a more western earthquake has increased. Has it increased the premium? I would put a very big question mark on that. Because the market in the Turkish market is still relatively small. If we think about that, a lot of the premium is influenced by the reinsurance costs an insurer has, and if we think that the Turkish market overall is easily, or a big Turkish loss is easily bearable by the international community, I would actually doubt that these modeling, although the models went up and got higher risk, I doubt that really this went through to the insurance market. Probably in some ways the opposite, because what we see there now since quite a while that overall the reinsurance costs are actually going down because everybody believes in this diversification and said, oh, we want more premium in Turkey because you know, we have to diversify our risk away we have in the US and other areas. So I wouldn't say that in science really brings premium significantly up unless we are in areas, for instance in the US, where a lot of capital is focused on. There, of course, people have to look very, very carefully into the cost of capital, and because there the capital cost is much higher.
Thank you very much. So I'm afraid that we have to close here this morning session. I remind you that the discussion can be continued in the panel. We've got the poster session now in the poster area XY, and you can read there. And then we continue this afternoon with the panel. And these are the panelists. Each of them is an expert in a particular field. We will try to cover everything: tsunami, earthquake, geology, finance, insurance, and even nuclear power plant incident. Thank you very much.